Hello, this video is intended to help draw some comparisons, some parallels between what we commonly call the long division algorithm and polynomial division, especially when you're dividing by a divisor that is a binomial or greater. So let's walk through a regular division problem just so that we can see what that process involves. Let's say that the divisor is 9 and the dividend is 2,313. There's this kind of step-by-step questioning process that we implement. Namely, we ask, is 9 divisible into 2? And the answer is no. Some people like to actually put a 0 there in the quotient. Others like to just continue to say, okay, well, can I find 9 inside of 23? And I think we can. There are two groups of 9 inside of 23. And here we multiply the 2 times the 9 and end up with 18. The difference of these two is now 5. And to continue the process, we bring down this 1 such that our focus shifts from asking how many 9s are there in this dividend to how many 9s are there now in 51. And I think there are 5 of those 9s inside of 51, giving us 45. Again, we multiply, and we end up with a difference of 6. Once more, we bring down the next number in the dividend, and we ask how many 9s are there in 63, to which the answer is 7. In this case, it so happens that 2313 is evenly divisible by 9, so the quotient is 257. So the beauty of this division algorithm is that it translates right over into polynomial division. So the problem we covered in class today was x plus 3, and we were dividing it into 2x to the third, 3x to the second, negative 4x, and 15. And the same kind of step-by-step process applies. That's why we call it an algorithm. It's a series of formalized steps. So now we're dividing this binomial x plus 3, and we realize we can't divide it into a monomial, but we can divide it into this binomial. And to kind of hone our attention, we ask, how many x's are there in 2x to the third? And that takes us back to our work from the previous lesson. This is essentially what we're asking. What's the quotient of these two? The answer is 2x to the second. So I put that 2x to the second here, and I find the product of 2x to the second and x. Of course, it gives me 2x to the third. The product here is 6x squared. And just like we did here, I'll be subtracting. So the difference of these two monomials cancel out. 3 minus a 6 is a negative 3x squared. And we bring down the next value here, the next expression, the next monomial. And now I shift my focus in asking what or how many of these binomials fit inside of this binomial, or how many x's are there in negative 3x squared. And the answer to that is negative 3x. So the product is negative 3x squared minus 9x. Once more we subtract. These two terms will cancel out. Negative 4 is actually being or having 9x added to it, which leads us to 5x. We bring down the 15, and we're nearing the end of our process. We now ask, can we find x plus 3 inside of this binomial? We can. How many times? 5 times. The product of 5 and x plus 3, 5x plus 15. And there's no remainder. So we end up with this quotient of 2x squared minus 3x plus 5. Some students today in class recognize that what we're really saying is that the product of the divisor x plus 3 and that quotient 2x squared minus 3x plus 5 is going to give us the dividend 2x cubed plus 3x squared minus 4x plus 15. So this long division or long division of polynomials is identical to long division of numerical values, and it means that we can take higher order polynomials and we can kind of chop them up into pieces. In this case, this third degree polynomial is the product of this first degree and second degree polynomial. And this is going to be incredibly important in the work that we do in the next few weeks. Okay, hope you enjoyed.